Hello and welcome to Introduction to Academic Research. My name is Ben, and today I will talk about significance testing. Assume you hear that the mean age of UCG students is supposed to be 21. But for some reason you have doubts about this claim and want to test it. So you want to check whether or not this idea, this claim that the mean age of students is 21, whether that's in fact true. Now, significance testing is a statistical method that can be used for exactly this purpose. In the context of significance testing, we often make a distinction between something that's called the null hypothesis and something that is called the alternative hypothesis. Now, in this context, the null hypothesis is what we want to test. So here, the null hypothesis would be that the mean age of UCG students is indeed 21. The alternative hypothesis is the fact that, or the claim that the null hypothesis is false. So in this case, the alternative hypothesis would be that the mean age of students is not 21. So the alternative hypothesis does not say the mean age of student is 22 or 23 or 19 or whatever. It just says it's the null hypothesis is false, right? It's not 21, whatever it is otherwise. Now, if we want to check whether or not the null hypothesis is true, one thing we could go about this is that we take a sample from the population, and then we check whether or not the sample significantly differs from what the null hypothesis says. And if it does, then we take this as evidence against the null hypothesis. So if the null hypothesis says the mean age is 21, and we take a sample, and the sample mean is 5 years, right? Then I can already say now it's very clear that there's a kind of a large difference, a significant difference between the null hypothesis and the sample we drew, and that means that we can see that there's something going wrong with the null hypothesis, right? If the sample is so different from the null hypothesis, then we have good reason to believe that there's something wrong with the null hypothesis. Now, the question is, what does it mean that something significantly differs, right? So that's a crucial question. And there's a way to make this formally precise. And to make it formally precise, we need to introduce two notions, the notion of a p-value and the notion of a significance level. And these two things we are going to discuss today in more detail. So first, we're going to look at what the p-value is supposed to be. Now, the p-value is the probability that we find a sample like the one we actually found in case the null hypothesis is true. So if we want to know what the p-value is, we assume the null hypothesis is true, we look at the sample that we actually found, and then we think, well, given the null hypothesis is in fact true, what would the probability have been to draw a sample like the one I actually got? Now, I put like the one in kind of quotation marks because this needs a little bit further explanation. What does it mean that the sample is like the one? Now, in this context, what I mean by like the one is that it's a sample with a sample statistic that is at least as far away from the population parameter, according to the null hypothesis, as a sample that I got. So in a way, what I mean is that a sample is like the sample I found in case it is as different from the claim of the null hypothesis as the sample I found. It sounds a little bit complicated, right, the sentence, but I will show you with an example what is meant here, and then you will see that it's actually not so super complicated. So let's look at an example. So assume our null hypothesis is that the mean age of UCG students is 21. And now I take a sample, and the mean age in the sample happens to be 18, right? So 18 and 21 is different, right? But it's not surprising in itself that the sample is different from the null hypothesis, because it would be very surprising if I find a sample that is exactly 21, even if that would be the real population mean, right? So our sample is always going to differ a little bit from the real population mean. That's not a surprise, but 18 is quite a bit far away from 21. So now we have to think about, well, does it significantly differ, right? And for that we use the p-value. So we ask ourselves, if the mean is really 21, how likely is it that we find a sample like 18 in this case? And what we mean by like 18 is, the question is the p-value, the probability the probability of the p-value is the probability that we draw a sample with a mean age in the sample that is at least as far away from 21, right, the population mean, according to the null hypothesis, as 18 is, the sample mean in this case, if the null hypothesis is true. So in this example, this means that the p-value is the probability to draw a sample with a sample mean of 18 or lower, right, or 24 or higher, because the sample like the one means samples that is as far away, right, but as far away can go into both directions, right? So it's either as low as 18 or lower, or as high as 24 or higher. Okay, so what is the p-value in that case? Well, to answer that, we have to we have to know what the standard error is. And let's just assume in this example that the standard error is 1. So what is the p-value in this case, right? What the standard error actually is will depend on the sample size, right, as well as the population standard deviation, right? So we discussed this before, right? So the standard error is the population standard deviation divided by the square root of the sample size, right? And let's just assume this is 1 for this example. Good. So if the standard error is 1 and our mean sample is 18, and the null hypothesis says that the population mean is 21, what is the p-value in that case? First, let's think about what the situation is like if the null hypothesis is indeed true, right? If the null hypothesis is indeed true, then the population mean will be 21. And if the standard error is 1, then the sampling distribution will look a little bit like what I have drawn here in the picture. Now, the next thing is we think about, well, what is the sample that we actually got? And the sample that we actually got was a mean age in the sample of 18. So that's the green part in this picture. Now, the p-value, for finding the p-value, we have to think about, well, what are the samples like the one, right? And like the one means at least as far away from the population mean as 18. So that is the pink area in this picture, right? So it's the samples that are 18 or lower, or 24 or higher. And the p-value is the probability to find one of these samples, right? One of these samples in the pink area. Now, how do I find out what this probability is? Well, we can use our old friend, the 68, 95, 99.7 rule in this case, and we use it to determine the red area, right? So the red area is everything that was not the pink area before. So, and we can use the 68, 95, 99.7 rule because in this particular case, 18 is 3 standard deviations, 3 standard errors below the population mean, and 24 is 3 standard errors above the population mean. And then the 68, 95, 99.7 rule tells us that the red area here covers 99.7%, and that means that the probability to find a sample in the red area is 99.7%. Now, if the red area is 99.7%, then the pink area has to be 100 minus 99.7%, and that is 0.3%. And that now is the p-value, right? So the probability to find a sample as far away from 21 as 18, that probability is 0.3. Good. Okay, now we know what the p-value is in our example, but that's not sufficient yet to say something about whether or not the findings are significant. Because to say that, we also need to define something that is called a significance level. Now, the significance level is a threshold that a researcher takes or assumes such that if the p-value falls below that threshold, then the sample is taken to be so surprising that it significantly counts against the null hypothesis. So the reason here goes as follows, right? So if the null hypothesis were true, then I would only find a sample like the one I have with a probability of p, whatever p is. Now, if p is very small, then it means it's unlikely that I find a sample like the one I found, given that the null hypothesis is true. But I did find this sample, so probably the null hypothesis is false, right? So given the sample I found, it's very hard to maintain that the null hypothesis is in fact true, because the null hypothesis makes a sample that I did find super unlikely. Now, it's good scientific practice to set the significance level in advance to carrying out the research, right? So it would be bad practice to first do the research, find a specific p-value, and then say, oh yeah, that's exactly the p-value I would have liked to see, right? Instead, what we do is before we go on and do the research, we say, well, I think that I should reject the null hypothesis if I find a sample that is this far away from what the null hypothesis says, right? And that's what the p-value specifies. Now, what's the p-value I should choose? Well, that's a little bit of a vague question in a way. The general guideline is that the more established the null hypothesis is, right? So if it's something that has already been substantially researched by lots of people with good evidence and so on, right? Then we need very, very strong evidence to reject the null hypothesis. And that means we demand a very low significance level that is a sample. We need to find a sample that is very, very surprising, right? Has a very low probability to be found if the null hypothesis was true. But if we research a hypothesis that is not so well entrenched in scientific findings, right? A hypothesis that is maybe already questioned by a lot of people, where there is already counter evidence towards, right? Then we would not set the threshold to be so difficult, right? So we would say a fairly high p-value would be sufficient to reject the null hypothesis. Now, in the example which we just looked at, we determined a p-value of 0.3%, right? So this means that if the null hypothesis was true, then we would only find a sample like this, like the sample we found, and like this again has this meaning which I specified before, in 0.3% of the cases, right? So here we could say, well, if the null hypothesis was indeed true, the sample we found was quite surprising, right? This is not a sample we expect to find if the null hypothesis is true. So if we, for example, have initially set the significance level to be 1%, right? then here we would say that the sample significantly differs from the null hypothesis, right? So the sample which we found is even more surprising than what we have set as a minimum level of surprise in order to reject the null hypothesis. We can also say in this case that the sample speaks against the null hypothesis at a 1% significance level. Now, it could also be that we have set us a more difficult to reach threshold for our research, right? So maybe the information about so in this case, we were looking at the mean age of students, right? Maybe the information we had was kind of issued by, I don't know, the university statistics something, right, where we think it's kind of trustworthy and we believe that they have all the information, right? So maybe in that case we would say, well, we need a very, very low significance level, because we would only suspect that the university would have made a mistake with something as simple as calculating the mean of students, the mean age of students. We would only really go out there and say, hey guys, you probably did a mistake there, if the sample is super, super surprising, right? So if the sample really is very, very different from the null hypothesis, right? And that means that, for example, we might have set the significance level to 0.1. And if that were the case, then finding a p-value of 0.3 would not mean that the sample counts significantly against the null hypothesis, right? So whether or not our sample significantly says something against the null hypothesis depends on two factors. First, the p-value that we calculate based on the sample that we actually find, and then the significance level that we initially set prior to starting with our research, and that we set depending on how impressive we believe our findings need to count against the null hypothesis. Now, today, empirical scientists are very careful about how strong they phrase their findings, right? So typically they would no longer say something like that their findings prove that a null hypothesis is false or something like this, right? Because scientists are aware that there's always this small possibility that they just happen to draw an unusual sample, right? If the p-value is 1, that means if you draw 100 samples, then one of those will be a p-value of 1, right? And it can just happen that you draw such an unusual sample, right? It's not impossible. It happens all the time, right? If the p-value is even higher, like 5%, something that's also sometimes used, right? Then that means that, well, 5 out of 100 samples will be so different from the null hypothesis, even if the null hypothesis is true, right? So for that reason, today people use a little bit more careful language. So they would say something like, the evidence confirms or disconfirms the null hypothesis, right? So even if I have a p-value of 0.5, right, that still kind of, it still draws into question the null hypothesis to some extent, maybe. Or a scientist could say something like, the sample allows or does not allow to reject the null hypothesis at a 1% significance level, or whatever significance level you want to impose. Good. So this is basically how significance testing works. I want to go over one more way in which we can use this type of reasoning, right? So this basically kind of type of statistical reasoning. I want to go over one more way to make use of this that is very, very closely related and works in exactly the same way, but sounds a little bit different. And that is, we can use significance testing also to check whether two groups of individuals differ in a particular parameter, right? So assume, for example, that you know what the average age of male UCG students is, and you wonder whether the same average age holds for female UCG students, right? So assume that the average age of male UCG students is 21, and you wonder whether the same is true for female UCG students as well. Now, in this case, your null hypothesis might be that male and female students do not differ in age, right? And this is where the term null hypothesis, I think, comes from, right? So previously it was kind of the term null hypothesis was a little bit surprising. Why would we say null hypothesis in that case, right? But here you can see kind of why we want to call this a null hypothesis, because the null hypothesis says there's basically no difference between male and female UCG student when it comes to age, right? So the null hypothesis might be that that male and female UCG students do not differ in age, and that means that the null hypothesis that the mean age of female UCG students will be the same as of male students, which was 21 in this case. Now, what we could do is we could take a sample of female UCG students and check whether that sample significantly differs from the age of 21 that is postulated by our null hypothesis. And if it does, then we might say, well, the null hypothesis is wrong. Female UCG students do have on average a different age than male UCG students. And if it doesn't count significantly against the null hypothesis, then we would say the null hypothesis cannot be rejected, or we continue to believe in the null hypothesis that being male or female does not have any influence on what your age is as a UCG student. Okay, so this is something that we're going to look at further in exercises, but the mechanism of making this type of reasoning works in exactly the same way as the example we discussed before in this lecture. Okay, that is it for today. Thank you very much for listening to these lectures. So this will be the last of the recorded lecture. I would already like to wish you best of luck with the exam that is going to be coming up soon. And see you around another time. Bye.